My Gavanan folks. Today we have an infinite series. We are interested in the sum over n from 0 to infinity of zeta 1 minus 2n over gamma 2n minus 1. So we have a sum involving both the zeta function and the gamma function. You guys know that this is going to be awesome, so here we go. I'd like to start off with the functional relationship between the zeta and the gamma functions, or wait, I would actually start with the functional equation for the zeta function. So zeta s equals 2 to the s times pi to the s minus 1 times sine of pi s over 2, gamma 1 minus s, and the star of today's show is actually zeta 1 minus s, because I'd like to solve this equation for zeta 1 minus s. So zeta 1 minus s, that's a horrible looking zeta. That's slightly less horrible. This is relatively better. So zeta 1 minus s equals zeta s over 2 to the s times pi to the s minus 1 times sine of pi s over 2 times gamma 1 minus s. And now for Euler's beautiful reflection formula. We do know that gamma s times gamma 1 minus s equals pi over sine of pi times s. And this, of course, implies that gamma 1 minus s equals pi over sine of pi s times gamma s. And we can use this to our advantage in the equation above it involving the zeta function. So this means that we have zeta 1 minus s, terribly sorry about that, and that does not look any better. Yeah, I'm not exactly very good at writing zeta. So zeta s, that looks pretty badass, I guess. 2 to the s times pi to the s minus 1 times gamma s is going to be upstairs, rather. So I have a pi over here, which means that I now have 2 to the s times pi to the s. That doesn't look half bad. And then I have a sine pi s over 2 term over here, a sine of pi s up top, and a gamma s on the side. And sine of pi s is actually quite advantageous because sine of pi s actually equals 2 sine pi s over 2 times cosine pi s over 2. So one of the 2's can cancel out, and we have zeta 1 minus s equal to zeta s times gamma s over what exactly? Well, we have 2 to the s minus 1. We still have a pi to the s term. And one of the sine terms can go away, so we're rid of that, and we're left with a cosine pi s over 2 term down there, or at least to the side. Okay, cool. That was absolutely awesome. What I'd like to do now is refer back to my infinite series and notice that we're interested in zeta 1 minus 2n, which implies that we should let s here equal 2n, n being any positive integer. And this implies that zeta 1 minus 2n equals zeta 2n times gamma 2n over 2 to the 2n minus 1 and pi to the 2n cosine of what exactly is cosine of n times pi, because the 2 goes away. So cosine of n times pi is actually equal to negative 1 to the n. So we now have this alternating term involved in the sum as well. So all of those zeta function acrobatics, and we now have s equal to the sum over n from 0 to infinity. Let's see, we have zeta, rather, I'd like to start off with the alternating term, and we have zeta 2n, gamma 2n, over, let's see, 2 to the 2n minus 1, pi to the 2n, gamma 2n minus 1. That's cool because, look, gamma 2n is actually equal to 2n minus 1 times gamma 2n minus 1, which is awesome because that means you have some cancellation happening. So I'll cancel out these two over here, and we're left with s being equal to the sum over n from 0 to infinity, negative 1 to the n times zeta 2n times 2n minus 1 over what exactly do we have? Oh yeah, we have 2 to the 2n minus 1, pi to the 2n, and that's pretty much it. I'd like to expand the zeta function now so that we have the sum over n from, wait, this was supposed to be from 1 to infinity. Am I correct? Oh yeah, have I actually written out the wrong sum? Yeah, this is supposed to start at n equals 1 instead. Terribly sorry about that. I'm sure everyone was at the edge of their seats thinking about, okay, what's he going to do about the zeta 1 term? Well, nothing. I just wrote out the wrong sum. So I'm just going to make some corrections. Oh yeah, this is cool. So we have the sum over n from 1 to infinity of -1 to the n times 2n minus 1 over 2 to the 2n minus 1, which is kind of annoying to write. So I'm just going to write this thing as, I'm going to expand by 2 so that I have 4n minus 2 here. Downstairs I have 2 to the 2n, which is 4 to the n. Or I could just write this as 2 pi to the 2n, which seems quite nice indeed. And I'm interested in expanding the zeta function, so I'll write this as a sum over k from 1 to infinity of 1 over k to the 2n. Of course, I can multiply out these terms so that we now have the double sum over n and k of -1 to the n times 4n minus 2. Yeah, my 4s look atrocious. I know, I've read those comments before. And I know it. You don't even have to comment it. I know it. So we then have, wait a second, we have 2 pi k to the 2n now that I would just like to write as 4 pi squared k squared to the n. Okay, cool. That looks not half bad, but it'll look better if I switch up the order of the summation operators, and you'll see why I'd like to do that in a short while. So we have me struggling to write the sigma operator, the sum operator, the sum over n now. And we have, wait a minute. I could, of course, multiply the alternating term and then use linearity. So yeah, I'll make that explicit later. We have -1 to the n for n minus 2 over 4 pi squared k squared over n. And now with the sum being over n, it looks like we do have a couple of geometric series on our hands, which is quite nice. So we have the sum over k from 1 to infinity, and we have 4 times the sum over n from 1 to infinity, -1 to the n times n, terribly sorry about that, over 4 pi squared k squared to the n. Then we have this -2 sum over n from 1 to infinity, -1 to the n, over 4 pi squared k squared again to the n. So we have a couple of series that need evaluating, and I'll start off with this one over here. So the template is the sum over n from 1 to infinity of -1 to the n times x to the n, which is, of course, a geometric series, with the first term being equal to -x and 1 minus the common ratio of -x. So that's 1 plus x over there. So all I need is to let x here equal to 1 over 4 pi squared k squared, which means that we now have the sum over n from 1 to infinity, -1 to the n over 4 pi squared k squared to the n, and this thing should equal -4 pi squared, wait, 1 over 4 pi squared k squared, that is, over 1 plus 1 over 4 pi squared k squared. Of course, after some simplification, we get -1 over 1 plus 4 pi squared k squared. So that is the first sum we're interested in. And for the other sum, notice that we have an n over there. So a template would should be the sum over n from 1 to infinity. What exactly? We have -1 to the n times x to the n. Rather, I could just start from 0 and then get 1 over 1 plus x. And if I just differentiate this with respect to x, we get the sum over n from 0 to infinity, negative 1 to the n times x to the n minus 1. And of course, that means we can start the sum at 1 now because n equals 0 just gives us 0 as a leading term. And this thing equals negative 1 over 1 plus x squared. And I know what you're thinking. We did not need the x to the n minus 1. And for that, we just expand using x to get the sum over n from 1 to infinity, negative 1 to the n times x to the n equal to negative x over 1 plus x whole thing squared. Again, we need to let x equal 1 over 4 pi squared k squared, which implies that the sum over n from 1 to infinity of negative 1 to the n times n over 4 pi squared k squared, which is of course exactly what we were looking for, is indeed negative 1 over 4 pi squared k squared over, let me see, now we have 4 pi squared k squared plus 1 over 4 pi squared k squared, and the whole thing is squared. So I'm going to have to expand using this thing squared, which means I should have negative 4 pi squared k squared over 4 pi squared k squared plus 1 whole thing squared, and that's our other sum. So after evaluating those two series, this is what the target infinite series looks like, and I now like to use the linearity of the integration operator, the summation operator that is, and the integral is just a continuous sum anyway, whatever. So we have now negative 16 times the sum over k from 1 to infinity, pi squared k squared, terribly sorry about that, over 1 plus 4 pi squared k squared whole thing squared, plus twice the sum over k from 1 to infinity of 1 over 1 plus 4 pi squared k squared. And I'm going to call this thing over here s sub 2 and this thing over here s sub 1 because that's the first sum I'm going to evaluate. So s sub 1 could be expanded as, you know what, I'm going to factor out 4 pi squared from the denominator. So we have 1 over 4 pi squared, 1 over 4 pi squared plus k squared, which looks dope. And to evaluate it, I'm going to need the help of one of my favorite infinite series results. That is the sum over k from 1 to infinity of 1 over k squared plus a squared, which as per my notes equals pi times a times the hyperbolic cotangent of pi a minus 1 over 2a squared. Now, in our case, of course, we just need a to be equal to 1 over 2 pi. So this implies that s sub 1 equals 1 over 4 pi squared times the sum over k. No, wait, I have evaluated the sum, of course. So now we have pi over 2 pi times hyperbolic cotangent pi over 2 pi minus 1 over 2 times 1 over 4 pi squared. Some lovely cancellations straight up. And then we're left with 1/2 of what exactly? Oh yeah, we have pi times hyperbolic cotangent of, oh wait, we're left with 1/2 of hyperbolic cotangent of 1/2 minus 1. So that is the result for s sub 1. Now s sub 2 looks to be a bit more tricky, but that's cool. I'll take out the pi squared term, and I have the sum over k from 1 to infinity, k squared over, let's see, 4 pi squared factored out, so that whole thing is squared. I'm left with 1 over 4 pi squared plus k squared, terribly sorry about that, whole thing is squared as well. So notice that I will have pi squared over 16 pi to the 4th power outside with some lovely cancellation taking place. And I have the sum over k from 1 to infinity of k squared over k squared plus 1 over 4 pi squared squared. Surely there is nothing we can do about it because we have like a squared term up top, k squared term, then there's a whole square in the denominator. No differentiation is going to help over it. So we'll just add a 0. And my version of 0 for this is 1 over 4 pi squared minus 1 over 4 pi squared, which looks absolutely immaculate in this lighting. So we have 1 over 16 pi squared times the sum over k from 1 to infinity of, okay, I'm going to club these two together and use linearity. So that means I have some cancellation taking place. I now have 1 over k squared plus 1 over 4 pi squared, which is exactly what I'm comfortable working with, minus 1 over 4 pi squared times the sum over k from 1 to infinity, 1 over, oh wait, there was cancellation over there, but no cancellation over here, which is still pretty damn cool. So wait a minute. I should probably do some simplification over here, just a little bit, just to make my life somewhat easier. So I do have 1 over 16 pi squared, which is just a quarter of 1 over 4 pi squared. And if I multiply that out, that 1 over 4 pi squared inside, I get the sum over k from 1 to infinity of 1 over 1 plus 4 pi squared k squared, which I remember is exactly what s sub 1 equals. Then I have 1 over 64 times pi to the 4th power, sum over, terribly sorry about that, k from 1 to infinity, 1 over k squared plus 1 over 4 pi squared whole thing squared. So I'm just going to leave it here. S sub 2 equals, well, a quarter of S sub 1 plus this strange looking infinite series that I now have to evaluate. And for that, I will once again reference one of my favorite results. So let me just take this, copy it, and paste it. Now, notice that I need a square in the denominator, which means I'm going to have to differentiate with respect to a. So let me just point that out. So differentiating the whole thing with respect to a, and then simplify the terms out.
Tomorrow.
Okay, everything looks sorted, and it is time to plug in a equals to 1 over 2 pi, and we should be home free. So we have the sum over k, terribly sorry about that, from 1 to infinity, again, terribly sorry about that, 1 over k squared plus 1 over 4 pi squared equal to, 4th power multiplied by 2, reciprocate the whole thing. This should be negative 8 pi to the 4th power. We should then have, okay, it's something similar over there, for some numbers, whatever, 2, yeah, 2 pi to the 4th power, hyperbolic cotangent of 1/2 plus, okay, pi squared now. Well, cancellation over there, 1 pi squared over pi squared, that's just a 1. So I have the hyperbolic cosecant squared of, wait a minute. Still have to expand using pi squared. Oh yeah, pi to the 4th power of hyperbolic cosecant squared of 1/2. This looks like one hell of a result, doesn't it? We're just getting started. So the result for S sub 2 was a quarter of S sub 1 minus 1 over 64 times pi to the 4th power. The good news is all the pi's go away, pi to the 4th powers, which I was going to forget if they were not being canceled out anyway. So yeah, that's actually advantageous for me. 1 over 64. God damn, why are there so many numbers in this video? So this implies that S sub 2 equals a quarter of S sub 1 minus sign, so that means all the signs are flipped, right? So 8 over 64, I think that's 1 over 8. Yeah, so that's 1/8 minus 1 over 32 hyperbolic cotangent of 1/2 minus 1 over 64 hyperbolic cosecant squared 1/2, is it not? Okay, that looks good. Now, finally, what was the infinite series I was even evaluating at the beginning? Okay, so after recollecting everything into what we were supposed to finally evaluate, we figured that this is S sub 1, right? So we have 2 S sub 1. Okay, that's actually quite nice. So this is 2 times S sub 1 minus 16 times all of this stuff up top. Okay, so that's minus 4 times s sub 1, again, negative sign, so that's minus 2. Then that's a plus 1/2, hyperbolic cotangent of 1/2. And there's a plus sign over there, 1/4 of hyperbolic cosecant squared 1/2. Okay, so that means we're interested in negative 2 s sub 1, which equals negative 2 times 1/2 of hyperbolic cotangent of 1/2 times minus 1. No, wait, there was a factor of 1/2 outside. Was there? Oh, yeah, there was. So there is cancellation taking place, and I like that. I like that indeed. So what I actually have is a negative sign outside, so that means this bad boy canceled out over here. There's a plus 1 and a minus 2 giving me minus 1. So I'm finally left with 1/4 of hyperbolic cosecant squared 1/2 minus 1. Wow, that was a wild ride. Definitely one of the best in the series evaluated so far on the channel. I hope you enjoyed the video. Be sure to like and subscribe. Drop me a follow on Instagram as well. Thank you. See you next time.